You know, at the very heart of pretty much every single chemical reaction out there, one thing has to happen. A chemical bond has to break. But here's the thing, not all breakups are created equal, which brings up a really interesting question.
Right. So, when a covalent bond, that pair of electrons shared between two atoms, finally gives way, what actually happens to those electrons? Do they part ways fairly, or does one atom just decide to take everything?
Well, it's kind of like a story with two totally different endings. There are two main ways this split can go down, and each one leads to completely different products and consequences. So let's get into this tale of two splits, starting with the nice, fair approach.
Okay, let's dive into path number one. We'll call it the fair split. Now, chemists have a fancier name for it, of course, homolysis. Think of this as the perfectly symmetrical, even-Steven way for a bond to break. And the name kind of gives it away, right? Homo means same, and lysis means splitting. So when a bond breaks homolytically, that pair of shared electrons gets divided right down the middle. One electron goes back to one atom, and the second electron goes back to the other. It's a clean, fair break. In chemistry, you've got to watch the arrows. They tell you the whole story. And for this kind of split, we don't use a regular full-headed arrow. Instead, we use this special half-headed arrow that looks kind of like a fishhook. Whenever you see that, it's a huge clue that only one single electron is on the move. Okay, let's make this real. Take a molecule like chloromethane. If we blast it with some energy like UV light, that bond between carbon and chlorine is going to snap. And look closely, you see those two little fishhook arrows? One shows an electron heading back to the carbon, the other shows the second electron heading to the chlorine. What we're left with are two separate, neutral pieces. So what are these new pieces called? They're known as free radicals. They don't have a charge, they're neutral. But see that little dot representing one unpaired electron? That single electron makes them incredibly lonely and unstable. They're on a desperate search for another electron to pair up with, and that's exactly what makes them so ridiculously reactive. All right, so that was the fair way. Now let's look at the other side of the coin, the unfair split. If homolysis was a friendly parting of ways, heterolysis is the messy, dramatic breakup where one side takes it all. Yeah, with heterolysis, sharing is not in the vocabulary. One of the atoms, specifically the one that's more electronegative, meaning it has a stronger pull on electrons, it just grabs both electrons from the bond and walks away, leaving the other atom with absolutely nothing. And once again, the arrow tells the story. But this time, it's not a fishhook. It's a standard, full-headed arrow. This symbol signals something totally different. It means an entire pair of electrons is moving together as a unit over to one of the atoms. So check this out with methyl bromide. Bromine is more electronegative than carbon, so it's got a much stronger pull. That full-headed arrow shows both of those bonding electrons just jumping ship and going completely over to the bromine atom. This leaves the carbon high and dry, and the bromine with a brand new pair of electrons. And what does that leave us with? Not neutral radicals, but charged ions. The atom that lost the electrons, the carbon in this case, becomes a positively charged cation, and the atom that took both electrons, the bromine, becomes a negatively charged anion. Okay, let's pause for a second. We've seen two completely different ways a bond can break, creating two totally different kinds of products. So let's put them side by side and really dig into the aftermath. I mean, the contrast is pretty stark, right? On one side, homolysis gives you these neutral free radicals defined by that lonely unpaired electron. On the other, heterolysis gives you fully charged ions, one positive and one negative. You could almost say one is a problem of loneliness, while the other is a problem of charge. So you'd think, okay, these things are polar opposites. They probably behave in completely different ways. But here's where it gets really interesting. There's a surprising similarity in what makes both of them stable. For free radicals, the rule is pretty simple. The more carbon neighbors it has, the more stable it is. A tertiary radical, which is connected to 3 other carbons, is the most stable. A primary radical with only one carbon neighbor is the least stable. It's like those neighbors help share the burden and stabilize that lonely electron. And now for the big reveal. Carbocations, they follow the exact same rule. A tertiary carbocation is the most stable and a primary one is the least stable. Isn't that wild? It doesn't matter if the problem is an unpaired electron or a full positive charge. Having more neighbors to help spread out that instability is always better. So the big question is, how does a bond decide which way to break? Is it just random?
No, not at all. It all comes down to the environment, the specific conditions of the reaction.
For the fair split, homolysis, you basically need to hit the bond with a ton of energy. And that energy usually comes from things like high heat or powerful ultraviolet radiation. Yep, like from the sun. These are the classic conditions that kick off what we call free radical reactions. But the unfair split, heterolysis, loves a totally different scene. It happens most easily in what we call polar solvents. And why is that? Because all those polar solvent molecules can actually surround the new positive and negative ions as they form, which helps to stabilize them and makes the whole breakup way easier to pull off. This is the hallmark of ionic reactions.
Okay, let's put it all together one last time. Homolysis, that's the symmetrical split. You use fishhook arrows, you get neutral radicals, and it's powered by heat or UV light. Heterolysis, that's the asymmetrical split. You use full-headed arrows, you get charged ions, and it's helped along by polar solvents. Two paths, two very different stories. So I'll leave you with this. The next time you see a colorful poster that's been left in a window and has been completely bleached out by the sun, you're actually watching millions of chemical bonds breaking. And now you know there are two ways it could be happening. The question is, which kind of split do you think is doing all that damage? Thanks for watching.